This is the continuation of IR spectroscopy topic. Now we continue with the explanation, with the interpretation of the carboxylic group. Here we can see that carboxylic group has carbonyl group, it has OH group, and the group, it has the interaction, the chemical bond between carbon and oxygen. So these three different colors belong to different three bonds: carbon oxygen double bond, carbon oxygen single bond, and oxygen hydrogen single bond. So here oxygen hydrogen single bond has this kind of wide spectrum as indicated here, and carbon oxygen single bond has this kind of absorption as indicated here, and carbon oxygen double bond carbonyl bond has the absorption as indicated here. So here in this table we can see the frequency, for example, for carbonyl bond ranging from 1680 1680 to 1769, somewhere here. Okay, and I would like you to pay your attention to this oxygen hydrogen double bond, which is not which disappears in the next sample here. We can see, this is another compound. This is an ester. In the first example here, we have the carboxylic group, and here in the next example we have the ester group. So the exchange of carbon hydrogen bond, as indicated here, which has this kind of spectrum, is disappearing because of the exchange of hydrogen with methyl group, as indicated here, with ethyl group, as indicated here. I'm sorry. Okay, I don't know, methyl or ethyl. Ethyl acetate, with ethyl group, it wasn't visible to me, ethyl acetate. So the addition of ethyl group to the oxygen, the exchange of hydrogen with ethyl group is causing the disappearance of the band belonging to carbonyl, belonging to oxygen hydrogen interactions as indicated here, and the carbonyl group and the carbon oxygen single bond absorptions are kept in the next examples as well, as indicated here. Okay, so by providing this kind of comparison, we can find out or claim about the presence and quantification of some some functional groups in the compared samples. And this is another good example. Here we have the IR spectrum of heptane 1, heptane 1, let's say, and heptine 1, as indicated here. I would like you to pay your attention to the presence of carbon hydrogen absorbance as indicated here, and here, which are present in all these three samples. The point is carbon and carbon, between this carbon and this carbon and this carbon and this carbon, the bonds are single bond. So it is different from this one. We are going to talk about it a bit later. Now what we have to understand, since they have these similar bonds in all these three samples, so here we can witness their presence. Okay, based on some differences in the third sample as indicated here. Here we can see a bit differences, compared to this one, but this presence of those signals were kept. And the carbon hydrogen interactions in the edging molecules, as indicated here with the red and green colors, are shown here. We can see, the red colors and green colors belong to carbon hydrogen interactions of the carbon located in the edge of the molecules. Okay, and uh, and the differences between the first one and the second one, as indicated here. In the second one, there is a carbon-carbon double bond in the edging part. Yeah, heptene one, and heptene one has one carbon-carbon double bond, and that carbon-carbon double bond is giving a signal of absorbance here, which is not present in the first examples. Okay, so comparing the heptane and heptene, by finding this kind of interaction, we can find out that this spectrum belongs to heptene, yeah, resulting from carbon-carbon interactions in this point. And another point indicated here in blue color belongs to carbon-hydrogen interactions. This is different from this interaction or from this interaction. This interaction belongs to carbon-hydrogen that has carbon-carbon double bonds between the carbons. Okay, that's why, since the heptane does not have any carbon-carbon double bonds, it does not have this peak, but the carbon-carbon double bond that having interactions with the hydrogen is showing this kind of absorbance, weak absorbance in this range of the spectrum. Okay, the pink color belongs to carbon-carbon interactions, and the blue color belongs to carbon-hydrogen interactions of carbon-carbon atoms. Okay, and in the third example, as we witness here, they have similar points as indicated here, and since it does not have the carbon-carbon double bond that exists here, since it has carbon-carbon triple bond, it is giving absorbance here, not here. So this one belongs to carbon-carbon triple bond, this belongs to carbon-carbon double bond, and this belongs to the interaction between carbon and hydrogen that has carbon-carbon triple bond. Okay? The interaction of carbon and hydrogen is giving this kind of strong absorbance resulting from the carbon-carbon interactions, which is not which is not specific to other cases. So we have to develop our ability to compare the compounds with the references, as I try to explain. So then we can develop our skills to compare IR spectrum, so then we can claim the presence of some functional groups in the given examples. And here we can see the molecular motions and the wave number of various groups: CH stretch, yeah, CC single bond, CH stretch of the carbon that has a double bond with another carbon, as shown here in alkenes. Yeah, and if the CH belongs to alkanes only, okay, it is around 2,850. Let's take a look here. 2,850, 2,850. Yeah, but if it has double bond as indicated here, here we can see it has the stretch at around 3,000 and 3,100. You see, so this is a good example to compare our understanding with this with these results. And carbon-carbon stretch isolated, or carbon-carbon stretch conjugated. They also have differences, even if they have a little overlapping points. CH band monosubstituted, CH band desubstituted, 1-1, or CH band desubstitute E isoform, CH band desubstituted Z form. They also differ from each other. They differ from each other by the location of some functional groups. You can find out on the net. I want you to understand another point, that this monosubstituted is quite highly differing yeah, differing quite highly from the D-substituted ones. And the stretch here, carbon-carbon double bond and hydrogen, carbon-carbon triple bond and carbon, uh, they might have this kind of close wave number, yeah, range. That's why many pointers should be taken into consideration while we are comparing the molecular motions and infrared spectrum of different aromatic or non-aromatic compounds. And these are while we are comparing the absorption of different functional groups, I wanted to say, and this is about infrared absorption of some functional groups. This is the continuation. I would like you to pay your attention to. Okay, did we talk about this page? Uh, yeah, we talked. Sorry. Okay. Let's take a look at this part. Here we can see the differences in the D-substituted derivatives in ortho, meta, and para condition. In ortho condition, okay, the wave number of absorption is between 735 to 770, in meta from 750 to 810, in para from 790 to 850. So there are differences based on the location of derivatives as well. We are going to give some exact results in the next pages. So what we have to understand from these results is that not only the number of substitutions, but also the positions of substituted functional groups can also affect the wave number and the absorption of the functional groups. Okay, Ketan. I would like you to pay your attention to the carbonyl group stretch of aldehyde and ketone. Carbonyl group stretch in aldehyde, carbonyl group stretch in ketone. Yeah, here in aldehyde, one hydrogen, there is one hydrogen, and here in ketone, okay, two other bonds belong to carbon-carbon interactions. So here we can see the differences here. In aldehyde, the wave number is around 1730 to 1740, quite a narrow range. And in ketone case, okay, it differs from 1705 to 1720. Yeah, there is exact difference between them, and there are no overlapping area. And in esters, here we can see the carbonyl group of esters. Here we can see the difference from 1730 to 1750. Yeah, even bigger compared to the carbonyl group wave number in aldehyde. Okay, these are the points that we have to pay some more attention while we are comparing the wave number of different functional groups as well. In haloalkane, here we can see big differences in the wave number from 500 to 750, because those halo derivatives can include chlorine, fluorine, yeah, iodine, or bromine. So the difference, I mean, the range is quite wide. And we can see in age interaction in amines and amides that are close or practically similar with each other. So sometimes it can be a bit difficult to find out the relationship based on the wave number. So in those cases, the other point is of the nitrogen, carbon, nitrogen, carbon, carbon, or nitrogen, oxygen, nitrogen, oxygen, carbon interactions should be taken into consideration to suggest the presence of different functional groups. Okay, next. And these figures enable us to more appropriately understand what we have been talking about in IR spectroscopy. Okay, here there could be, let's say, three hydrogen atoms, and this is hydrogen, yeah? And these interactions might have wave number in this range from 2,850 to 2,960 reciprocal centimeters. And if this hydrogen is replaced with methyl group, as indicated here, here we can see the shift from, let's say, 3,000 sphere to 800 to 1,300, yeah? Here from 2,550 to 2,960, it is shifting to much lower, let's say, wave number reciprocal centimeters. Okay, and if it is in alkene case, we can still see this kind of differences. Carbon-carbon double bond and carbon-carbon double bond. Yeah, here we have carbon hydrogen and carbon-carbon double bond indicated here. Let's say one hydrogen is replaced with, let's say, okay, this part should be actually given in the red for a better understanding. Here we can see the differences between this functional group and this functional group, and here we can see the differences, big differences between them. And we can compare like a hydrogen, 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 carbon, carbon double bonds with hydrogen, hydrogen for this carbon and hydrogen methyl group, for example, case. Yeah, the exchange of one hydrogen, the change of one hydrogen with a methyl group, in this case, for example, causing the wave number, yeah, absorption from 1,640 to 1,680 to 910 to 990. Yeah, big differences among them. And the replacement of two hydrogen of one carbon as indicated here is causing even smaller wave number as indicated here. Okay, in aromatic compound, this similar thing is could be observed as well as indicated here. And here, in this case, we can understand this thing is even more appropriately. Yeah, we talked about these changes. If the mono-substituted, let's say, derivative has wave number in around 1,900 reciprocal centimeters, yeah, the replacement of this hydrogen as indicated here, leading to the formation of 1,2 cis derivative causes the wave numbers to be much smaller. That has a wide spectrum from 750 to 650, something like that. Yeah. Or if they are not cis, they are trans, for example. Yeah, the vibration might cause to be shifted from 1,000 to 950, 960 as the middle number, yeah, as the median number. I would like to remind that cis compounds are more stable. Since they are more stable, here we can see much lower vibration. This is one of the reasons that causing higher stability of cis compounds compared to the trans compounds. Okay, good. Okay, this is about 1,2 derivatives. And here we can see 1,1 D-substituted or tri-substituted or tetra-substituted compounds. In 1,1 D-substituted compounds, here we can see the shift from 1,000, 9,000, from 1,900 to somewhere like 870, yeah, of the medium number. And in three substituted compounds, 1, 2, 3, one hydrogen is only remaining here. We can see even smaller wave number. In tetra substituted derivatives, we can see the complete disappearance of the samples of the wave number that could cause the absorbance of infrared light. And this is another example in aromatic compounds. In aromatic compounds, if we have a monosubstituted compound that has the wave number around 700 or somewhere like 640, 650, yeah, and the addition of another, let's say, functional group like the formation, like causing the formation of D-substituted derivatives in ortho, meta, and para condition. Here we can see the changes in shifts. If it is mono, let's say, I mean, if it's ortho, let's say, uh, derivatives, we can claim about higher stability of this compound, yeah, as of monosubstituted derivative, because the vibration is not increasing. Yeah, the vibration of the skeleton is not increasing. But if meta and para desubstituted derivatives are obtained, here we can see much higher wave number, yeah, much higher wave number that could be linked with the vibration, and that could explain the lower stability or higher vibration, yeah, of those, let's say, aromatic compounds. And if the compounds are three substituted, 1, 2, 3, as indicated here, 1, 2, 3, or one, I mean 1, 2, 4, or 1, 2, 3, as indicated here, or 1, 3, 5. So here we can see non-linear changes. Yeah, we can see that the wave number differ from each other in non-linear, let's say, logical way. Here we can see the differences between 1, 2, 4, or 1, 2, 3, or 1, 3, 5, 3 substituted derivatives. Okay, in general, I would say that in aromatic compounds compared to the monosubstituted derivatives, the addition of another okay, D or the formation of D or 3 substituted derivatives in general cause the higher wave numbers of the infrared, let's say, absorption. Next. Okay, this is about strength of the intensity. What we have to understand from this table, that the intensity of absorption in different wave number in different compounds like alkane, alkyne, alkyl halides, alcohols, or arenes, aromatic rings, amine groups differ from each other. They can be qualified as medium, strong, or weak in some cases in aromatic compounds. These are some other pointers that we have to take into consideration. And this is a good example that I try to deliver in pages, in previous pages, that the carbonyl group have wide, let's say, absorption ranging from 1,000 1670 to 1780, right? But in specific case, the peak, I mean, the absorption is quite narrow. For example, the carbonyl group in aldehyde has 1770 wave number. In ketone, 1715. In ester, 1735. Okay, they have the deviation, of course. I think this is the medium absorption numbers for these compounds. And in amide, yeah, it has 1690. In carboxylic acid, 1710. In all cases, they are of strong intensity, but they have quite highly differing absorption in absorption of carbonyl groups in different compounds. Okay, where we use infrared spectroscopy. We have been discussing only the identification of functional groups. Actually, the Fourier transform IR or IR spectroscopy can be used for the interpretation of graphene-based nanoparticles, biomolecules, metal complexes, and their nanoparticle interactions, drug cell interactions, cell cell interactions, or structural elucidation of small molecules and natural compounds. Yeah, IR spectroscopy can be used for protein structure analysis, drug analysis, environmental monitoring, yeah, polymer characterization, and some other approaches can be developed by us. As we know, the capabilities of IR spectroscopy, and as we have some skills to analyze IR spectrum, we can develop our own approaches where we can use effectively in different to interpret the results of different, let's say, experiments. And what we have to understand from this is that IR spectroscopy is non-destructive. We have talked in our previous lessons that UV can cause mutation, UV can cause the breakage of covalent bonds. And that's why, okay, it can be considered, UV can be considered as kind of destructive approach, but IR is non-destructive approach. It does not cause the breakage of chemical bonds, or it does not cause mutations. Okay, if the intensity is very high and long term, it might cause mutation as well in some cases, but compared to UV, it's very of low level. And it requires a small sample, and it is highly specific, as we have been discussing. And limitations can can include that IR spectroscopy does not detect cannot detect, let's say, nonpolar molecules easily. And overlapping peaks, as I have been discussing, overlapping peaks can complicate the analysis. This figure was obtained from this paper published in one of Springer Nature journals. As indicated here, nanoscale infrared spectroscopy is a non-destructive probe of extraterrestrial samples. And from this figure, we can find out about how we can carry out how we can obtain the IR spectrum of the compounds. For any case, if we are learning the IR spectroscopy of some natural compounds, it's better to crush by using mortar and pestle, and then it can be seized to obtain more homogeneous sample. So then the IR spectrum of it can be obtained. Here we can see the absorbance level in previous pages. Let me show you one example. Here these are about the transmission. So 100 belongs to transmission, and this belongs the absorbance, and the higher absorbance is linked with the lower transmission level. And in this case, here we can see this is about the absorbance. Yeah, high absorbance is the one that could be something like this if we see the transmittance level. So this is about how IR spectrum is obtained, and here we can see that not only spectrum is useful to us, but also by using IR, we can obtain different images as indicated here. This is the IR image representing the distribution of the carbonyl stretching vibration integral and intensity. So we can obtain IR images of many samples, and comparing to the IR image of the reference sample, we can claim some our, let's say, suggestions about the presence or absence of some functional groups by comparing to the IR image of the reference sample. And again, uh, based on the fingerprint region or based on some other regions, we can claim about the functional groups as indicated here. I'm not going to repeat them all. Triple bonds belong to this region, double bonds belong to this region, and this the region belonging to hydrogen interactions with nitrogen, oxygen, or carbon. Yeah, and this is about the FTIR. FTIR, Fourier transform infrared spectroscopy, is kind of faster and more sensitive than traditional IR because it uses interferometers instead of monochromators. So it produces more resolution. It produces a higher resolution. It can be measured faster and better signal to noise ratio. So this is, let's say, a more updated version of IR spectroscopy. So the spectrum obtained by using FTIR can look like something like that, and it can be of higher resolution compared to IR spectroscopy. And here we can see how we can interpret the results compared to different results. Okay, this is, for example, the IR spectrum of the tissue, let's say the skin tissue, yeah, epithelial tissue. And we have the IR spectrum of albumin that looks like this. Yeah? Here we can see the high percentage of NH or OH or CH in these cases, right? Comparing our tissue results, IR spectrum, with the one belonging to albumin, here we can claim a high ratio of protein because NH belongs to protein in many biological, let's say, samples. So by comparing the epithelial tissue IR spectrum with the one belonging to albumin, then we can make a kind of claim about the presence of a high ratio of protein that belong that was studied in an example of albumin. Yeah, and here we can see amide group, amide 1, amide 2. Yeah, and some others, and we do not see some specific let's say wave number belonging to urea in this example. So this is one example that how we can compare this, how we can compare different samples and what kind of suggestions we can develop by comparing them. And I would like to remind you that UV causes high energy differences before and after absorbance and emission, let's say. So here we can see different energy transmission in an example of electrons jumping from the ground state to the excited state. In case of IR, we do not see this kind of differences in the electrons. Electrons are expected when we treat the matter with IR. Okay, we do not expect the electrons to jump from the ground state to excited state. Instead, molecules are excited, and molecules get more vibrational energy. They are excited with the, they are excited, and the IR causes more vibration of the molecules. This is the main difference between IR spectroscopy and UV spectroscopy. And among them, based on the energy transmission, there are, okay, Rayleigh scattering, Stokes Raman scattering, anti-Stokes Raman scattering, or anti-Stokes or resonance Raman scattering, as indicated here. Yeah, we might learn, hopefully, these physical methods of investigations as well in the future. And these are all. I hope that the lesson was useful to you. To those who are watching us on YouTube, I ask you to support us with your likes, so then these video lessons can reach a wider audience. This is all. Thank you for your attention. Have a good day.